So let me introduce the panelists again. So we have Professor Evangelist Gergo from Tokyo Tech. We have Professor David Su from National University of Singapore. We have Professor Li Ka-shek from CMU, and we have Dr. Kylan Garrett from NVIDIA, and Professor Brian Bencher from Bernard College and Dartmouth. So I think to give some time for the audience to think of some questions. We start with some question that we prepared. So the first question we have is for Professor Su, actually. So you have followed motion planning and control for a long time now. Can you share some thoughts on these recent advances in parallelization and motion planning and control, and where they might take us?
Oh, working on this for a long time. You made me feel really old. Okay. Given all the excitements in the field today, I think I'll try to sound as young as possible. I think that if we try to think about what's to come, and we have to put it in the context, right? So today's context is data-driven robotics, machine learning, and big data, big compute, right? How does that affect motion planning and control? I want to make a quick observation over here. I mean, it's great to see that there's this room full of people over here. I was earlier in another workshop, which is more data-driven robotics. They were giving a much larger room, but the number of people there, I estimate, probably is similar to what's over here. So what does that say? I think that says that one is the organizers' prediction about what is to come. That's why they are given a bigger room. The other one is what's actually happening and what's actually needed, which is indicated by the number of people actually in the room, and which is kind of similar, right? So I would say that now, if we think about motion planning and motion control, at least in a classic sense, we think of that as model-driven approaches, right? So now one of the we have heard wonderful talks about all the algorithmic advances for them. Now, one thing that, based on my experiences, was that in practice, one of the big challenges actually for model-based approach is how do we get the models? And that is a real challenge. And today, I think given the large amount of data, that can potentially help, right? And we can today, because of the advances in machine learning and so on and so forth, we can use maybe sometimes data directly and skip at least partially of the modeling process. This is something that I think that will be very exciting to connect model and the data, and to a substantial extent that the model is a compact summary of the underlying data. And in our earlier days of motion planning and control, we often assume that that model is given to us, and then we do the algorithmic work. And today, I think we really should go to the origin of the model, which is the data itself. I think that is one thing. And the other thing that now, when we try to process a lot of data, of course, that we need computers. And today, I mean, GPUs and parallelization, these are all wonderful things. Now, one abstract way of thinking about planning is just a search, right? The search tree. Now, if I have parallelization, I can fire off a lot of traces along the tree, and that would actually reduce computation time, because the model computation parallelization is just the depth of the tree. Then if I can fire off lots of being parallel, that is great. And that reduces computation time. But it doesn't actually reduces the total amount of computation needed, which is the amount of power that the processor would consume, right? So in addition to time, another notion of computation efficiency is the power consumption. And let me give you a concrete example over here. So we are running our little robot dog, and we put an autonomy stack on top, and try to run the robot system. And suddenly we felt that we realized that the total operation time of the robot has been reduced by almost a half. We couldn't understand it in the beginning why that happened, because originally we thought it's just the difference between spec and the new reality. I mean, spec says it's 1 hour 45 minutes. We actually were able to run slightly below below 1 hour or something. But when we try to teleoperate it and everything was still fine, it's 1 hour 30 minutes. It's only that we run the autonomy stack that is only like 45 minutes or something like that. And we found out that actually it's a JSON that consumes almost half of the power. Now, I would normally imagine that is, I mean, the computation power consumption is probably 1/10 of the mechanical power required to power robots, but actually today it's a lot more than that. It's almost 50%. I think that is the challenge, is that even if we can do parallelization and to reduce computation time, and I always make a challenge still remains to reduce the amount of total computational load, that those challenges still remain, I think.
Yeah, I think there's still a lot of work to do to reduce the amount of computation in general, based on the model of motion planning and control stack. Okay, so the next question is kind of related to the MPC and Kinofax MPC, Kinofax PC. So the question is that now motion planning time has been significantly improved to like the range of milliseconds. And normally when we solve control input, right, we also solve in milliseconds so that we can send the control input fast enough down to the motors. So with this new development, what do you think about the roles of planning and control in an autonomy stack? Do they merge together, or it's like become one, or not maybe? And what are the like challenges that people might encounter if they have to do like planning and control, and both of them are really? So this is for like everyone. Yeah, please.
Is model, predictive, control, right? Let's agree on that. So it's model, and any technique that uses a model, predictive, right? And you re-optimize, right? It's an implicit form of feedback. So I just want to say that for sometimes in communities, we come up with new names, we create entire branches of research to realize that at some point it's the same thing. So model predictive control works. Control theorists may not like that necessarily, but it does work. Optimization is great. I mean, what the thing that excites me is all of the work that people do in reinforcement learning, bringing MPC planners into reinforcement learning. This is really great work. Like, we should be asking what are the papers that we would like to have written, and I would like to be the author of one of these papers. I think this is really great stuff. Yeah, I think the robotics community is a very decent community because we have always the hardware next to us, and it's always great to be able to go quickly from software to simulator to an actual real system. I do have an issue with a lot of people who go out and talk about general intelligence and the use of neural networks as planners and stuff like that. I do agree with the fact that MPC will be the heart of a lot of the autonomy and planning, but then actually also demonstrating it on a real system consistently is also important.
Yeah, it's interesting. A lot of neural network-based controllers still require some sort of underlying primitive controller. Like one classic thing is task-based controllers that can convert poses into torques, right? And so many times we see when we kind of intersect with the imitation learning crowd that they degrade in performance aggressively to get closer to the true action space, right? And so it's always interesting to kind of think about how there's this promise that we'll just solve robotics with these methods, but they still require a lot of conventional control underneath the hood to be effective in practice.
Yeah, I mean, I'm talking about the fact that even if you do imitation learning, there's nothing that guarantees you from not violating constraints, right? And so it's not about how you put things together, learning with NPC. It's more about actually going into the architecture of the learning module and see how you can embed these constraints there. And that's not going to be like it's just like a feed forward neural network, or it will be something more than that.
Or a neural network that controls an NPC loop or something, right? Can tune the costs.
Yeah, I think I'm really like excited about this optimization for neural network architectures in the spirit of physics-informed neural networks. I think this is really the way to go from my perspective.
Well, and I think you're also getting at this sort of hierarchy thing here, right? Which is sort of like how many layers of controllers, planners do you want, right? Because if you look at many of these papers, they'll be like a high level, a mid level, a low level, a super low level. And by the way, we're forgetting that there's like an embedded controller at the motor converting like a theoretical torque into actual, you know, electrical signals, right? So what's planning, what's control? Does it really matter to some degree, right? Like we want to take in the environment and we want to put out the right signals.
It's more about the synchronization of or the coordination of these modules that I think it's really cool research area.
And also,
Since we're talking about the hierarchy, I think it's nice to be able to have a hierarchy, and it allows easier algorithmic decomposition and so on. But in reality, when you're trying to build a very reliable system that works all the time, the inconsistencies between the hierarchy and different levels is really hard to overcome. The more we can strive for algorithmic homogeneity in there, the better. Now, of course, I don't believe that, you know, planning control all the way to the goal, it actually makes sense for many applications. I mean, we as people, we just don't, you know, reason with the full dimensionality all the way to the goal very often. And on top of it, I totally agree that the model is, you know, as you go farther and farther, so to speak, it's typically becomes worse and worse. Like what the humans are going to do in 30 seconds from now is just, you know, it's very hard to predict. So there's no point in kind of reasoning about that to the full fidelity. But having algorithmic frameworks that try to get away from decoupling and instead have a tight coupling that where you can provide strong guarantees and all that stuff is very important for the product. That's my view.
I would actually go a little bit further than algorithmic homogeneity, but to go all the way to mathematical homogeneity, right? So one way to distinguish between the neural network control and let's say MPC is that to think about the underlying function class that connects the input and the output. Now, the current neural network, let's say transformers, right? They are general purpose function approximator. They're very, very broad. Now, in order to capture all the physical constraints, because the functional approximator itself very general, therefore you have to sufficient data in order to narrow it down to the specific class of the physical phenomenon and constraint we need to capture. That is not exactly usually happens in MPC. In MPC, we take advantage, optimization. We take advantage of the structural constraints of the class domain and using function classes much better fitted to that. That's why we can enforce those physical constraints much more accurately and forcefully. And this trade-off in general will forever exist.
I mean, there is work that the dynamics of the transformers will arise from objective functions, right? There are papers that have shown that, but these objective functions will have nothing to do with the objective functions that you care about a real actual system. They are mostly tuned to get the underlying architecture. Right, so that's right. That just to be.
Great. Maybe we can switch to the question from the audience. Okay. Yes.
Yeah, so I have a question for the panel regarding this idea of in the era of massive parallelism, what is the trade-off between model fidelity versus the speed you can query your model? So So I can give a very concrete example, so for the DARPA Racer Challenge, I talked to Byron Booth about this a lot, right? I know for the Racer Challenge, probably not for Overland, right? So what they're trying to roll out is using a very simple unicycle model, or maybe bicycle model. Very simple, but Byron's idea is if we have a very efficient model, we can run it very quickly, then it can compensate for the lack of fidelity of that model, right? But on the other side, our lab is trying to explore a lot on the other extreme of the off-road mobility side. So if you have extremely rough terrain, I think about all these hobbyists who drive jeeps over those rocks. We call like rock crawling, rock scaling, right? So the dynamics is extremely difficult, it's extremely complex, and also you need to consider the underlying geometry of the terrain. Then that model, if you want to build high fidelity, it's a very big model. Then using MPPI, we have this trade-off of, we need to balance how accurate you want the model to be and how quickly you want to query your model. Then you need to really try, that's a lot of trial and error from our.
They're both right.
Yeah.
They're
I guess-
both right. They both approaches are right, right? Like, so it really depends also what kind of, I guess, precision you want to have, what kind of skills you want to have on the autonomous system. Be really very like precise. You want to use the model and be slower. But if you want to go super fast, then you can use it simpler. So this trade-off that there's no, I don't think that there's a theory about it.
There's no theory behind this, any highlight, high level ideas, because what we are trying to study is really, is there a sweet spot between them, like between these two extremes, like some reasonable fidelity of the model, and it's not too slow, so that can give, we actually have some very interesting experience. Right now in our lab, we have lots of different MPPI based planner based on different models. We actually find out like the simplest model, not the simplest, like there is a middle ground in the middle, not the bicycle model. It's actually a model, it's a 6-off vehicle, ground vehicle model. We decompose into 3 different parts. One is the bicycle model for X, Y, and yaw. And then elevation, the Z is for the elevation map. And for the yaw, roll, and the pitch is basically neural net prediction. So that is not a very precise model to begin with, but very quickly for you to query. But that is still the best performing overall when you put it into an autonomy stack. But I was just wondering if any thoughts on is there any principle behind this? Can we think about what's the trade-off, especially under the lens of massive parallelism? We have lots of computing we have. What's the best way to go about this?
Very good.
I think I agree that they're both right. Like this question is very related to the question that I often get. What is it better? Is it better to do just replanning all the time, or is it better to do proactive planning on the uncertainty? It's very much dependent on the specific problem that you're looking at, the domain that you're looking at, and all that stuff. Because if we're talking about say just navigation in open areas, then replanning will just work fine. Like if you deviate a little bit, it will just do fine. It's very related to like a PC type of approaches. If you're looking at I don't know, let's say planning in for military missions where there is there's uncertainty about certain vehicle dynamics, and then that may lead to really bad outcomes, then it becomes much more important to actually reason about that uncertainty ahead of time. I think this is also one of those places where ML could be really helpful to actually learn from kind of a offline training and all that stuff to actually predict where you want to have just this deterministic replanning as opposed to proactively. And the same thing, a lot of uncertainty actually comes from the fact that you're not using the full fidelity models, right? And it's like that's very related, and therefore whether you use a simple models that are very fast to roll out, but at the end of the day, you get a lot of uncertainty what's going to happen, whether you use high fidelity models that are very expensive to roll out, but they capture a lot of different things. Kind of learning which ones and when to use, this actually can be very helpful.
And sometimes, do you want to go ahead? Yeah, sometimes it's nice to use an overly conservative low fidelity model, like going back to what Fabio was talking about with the Kurovo and Kutamp projects and the collision representation that were kind of forced by using GPU hardware to do sphere to mesh collision checks. And so there's the question of how do you approximate your robot in your environment with spheres? Anything that moves needs to be a sphere, basically, right? And so you can, in the limit, make infinitely many spheres and have a really good approximation, but that then, eats up computation, right? And so many times we choose closer to 25 to 50 spheres per link, right? But then is overly cautious many times, right? And so then you might not be able to solve some problems that you otherwise would be able to solve with the mesh collision checker.
Well, but and I think like let's make it even one more step harder, right? Like we're saying that it depends on the timescales of the problem and the timescale of your solver. It also depends on, well, how nice is your computer, right? If you get a slightly nicer computer, now you can probably go a slightly nicer model, right? So I think this is like sort of a constantly moving target. I don't think there's an answer, but it sounds like, again, there's all these nice little middle grounds, and unfortunately, or fortunately, there's good research to do. Actually, fortunately, there's good research to do. We need to figure this out, right? There probably is a theoretical something that says, like, if your system operates at this time scale and your noise from your perception and mapping stack is at this time scale, and you need to be this precise, then you should be this precise in your model. But like, that's a series of nonlinear optimization problems that are all NP complete that you have to simultaneously solve to come up to the correct solution. I have no idea what the answer is, but like there probably is one, right? That starts to get you in there.
I really agree with you guys, especially kind of on, you can be more conservative, right? But what we are trying to push in the lab is motion planning under extreme mobility, right? So one is the rock crawling thing we talked about. The other is high speed, just like the racer program. Another one we have been running is this called the benchmark autonomous robot navigation challenge. It's a competition we run. But lots of obstacles around. You have to maneuver very, very precisely. Then the problem becomes whether your model is precise or not, because if a tiny little bit error will cause you to collide with obstacles, say 2 centimeters to the left, right? So one approach we're trying to, so going back to the trade-off here, we have one work we were thinking about is, can we try to decrement the dynamics fidelity along the way? Because you probably don't care about the dynamics fidelity like 5 meters into the future. You won't be precise anyways. Your error is accumulating to a degree that you don't care that much. So this work is called decremental dynamics planning, so DDP. So that's kind of like a very brute force. Yes, another DDP.
Well, and there's already some work, like, so Patrick Wensing had like a Cafe NPC paper, and they showed the same sort of thing, right? And there was a couple other things that said.
So I guess how can we balance in the middle? And of course, then how do you decrement? How do you decrement that? That's another question to ask. As you mentioned, a lot of research opportunity here. I just want to get everyone's thoughts on how we trade off.
If you think about it from the controllability perspective, which is unfortunate, but most of the things that we have, I would say, for linear systems, right? But what does controllability tell you? It tells you what are the states that you can reach within a finite amount of time, right? And then your model somewhere appears, right? And so then when you choose models of different granularity, your controllability changes, right? But rightfully so, because you might not want to be extremely precise, right?
So we have another question.
Yeah, no, it's kind of a follow-up from this extra question here, because so far we've been talking about a model, right? And I think we are in a parallel computing workshop. What about many models, right? What about a set of models, each one super fast, but capturing different parts of it? Can we think about this problem as also a parallel set of models with a set of controls?
And what's the variation that you need, right?
What's the variation what you need? Is that physical parameters that you vary somehow, right?
There's some really interesting work that I've seen.
It's like domain randomization.
Well,
It's connected to that.
yeah. But it's online, right? But what's the difference really between learning and optimization, right? It's the online versus the offline. So then there's also a question really on how much are we caching to some degree, because SGD is just highly inefficient, but like gets there eventually, right? And we're trying to do, so I don't know, like I think all of this stuff is sort of tied. And there is some work on linear to nonlinear gap quantification. And there's some, sums of squares certification and some other things. Sylvia Herbert's group has done some stuff recently on newer methods that are faster, right? Maybe we need to be looking at that to understand where the gaps are to then insert the uncertainty correctly. Yeah, because I think you're right. I don't know how to do it. I tried one random thing. It worked pretty well. We should probably try some more and like prove it.
But there also works on the pure planning side, taking a number of models, all of different fidelities, all of different associated computational costs of using them, and trying to, within a plan, trying to reason which one to invoke. And that's also kind of somewhat related to like lazy planning and all that stuff. And to provide guarantees on what you get out of it. I think it's very relevant.
It's also related to solving a number of problems simultaneously, right? That if we're going back to the domain randomization question, what if you're able to produce trajectories that are demonstrations for some sort of system across 1,000 problems all at once on a single GPU, right?
I think we have time for one or two more questions.
I'll make a comment from industry perspective, because I work on many autonomous. I develop autonomous systems. I work on autonomous driving, self-flying airplanes. So when we design, when we try to make a design choice for solving a autonomous problem, so we have a group of classical people, they know motion planner, they know behavior planner, and they try to solve the problem by using a hierarchical network. And there's a group of people, they like to use ML all the time. And then we have to make a choice. And then you start to consider development time. So regardless of the performance, you see how early we can develop this. So for me, I'm motion planning the block of a bigger system. You can implement it in 3 weeks, but then you have to tune. And then you have to work on the behavior planner. So each requirement constitutes a mode in the behavior planner. And for that mode, you have to have a different cost function. So you spend so much time to develop this classical approach. By the time classical people to tune their cost function, by the time they spend time on the behavior planner or like all this mode transition, all the field tests, ML people, they just collect data. And they let their test vehicle collect lots of data and they train their model. And within a short amount of time, they can show nice performance. And then after preliminary tests, they say, okay, we will go with the ML approach. So I have, maybe like I like classical approach because they are interpretable. But when you consider development time, because in regards, yeah, no, but what I'm trying to say, like decision makers, they say we have a project, we have a product, we have to go to market very early, maybe earlier than other competitor. And then in the early phase, they have to commit a design approach. And then usually they say, in 3 months, let's do some exploration. And then ML people usually come with better performance. Although we may do as classical people better in the later, but then they commit on one approach. And then we start to see all ML people are dominating the approaches. So that, like, I'm just trying to say, like, we are working on motion planner, we have to make it faster, run it faster. But how easy is it to, how early we can develop these things and we can survive against these ML people?
Like, thank you for so much for sharing us this insight from the industry and how things evolves, right? But what do we learn from this? When you say the ML people or ML system showing better performance over what, right? Over the entire the generalizable domain of performance, or over some narrow specific preliminary test set.
So
right? If it's only the latter, right?
The thing is, like, in the company, they also make investment for infrastructure. So ML people, they come up with one pipeline, they can work on many product lines. So they say, I can use same approach for solving a human motion planning problem, for autonomous driving motion planning problem. So like, but for classical people, they have to come up with techniques to collect, model their system. They have a team, they have to spend more time. So like, they kind of say, we can have an approach, we can apply to multiple problems without that much change in the engineering work. We just need to collect data, we'll test, we'll simulate, we'll train. So that's their defense. And usually, big CEOs, they like that approach. They say, one tool that can work on many problems. So that's why we cannot survive against them.
They promised that. I don't.
No, I like classical approach. I'm also doing
No, that's fine. But the point is that when they claim they can do this, right? They claim they can do this. Is there any evidence, empirical evidence, they succeeded in doing this, right? So a single development pipeline that can succeed in a wide variety of different robot systems. Has that happened yet? Have we seen experimental evidence of that? I'm asking you the question. I'm not trying to ask rhetorical questions claiming that the ML people hasn't developed this. I'm just asking a neutral question here. Has that happened yet or not? Right? So we are now, if it has not happened yet, then we are waiting for the experiments. And then the other thing is that for the decision makers, right? And it's for them to not just see the promise of something, but make a balanced decision, because one day that product will be deployed out there, and we'll have to expect generalizable performance and not the unbounded extrapolation from a small test set, right?
Professor Lee.
So, yeah, so they've. I mean, I've seen that a lot as well, absolutely, 100%. I think one of the things that needs to happen is the education of the folks who make decisions, including the DCs. I think there's a lot of it is just comes down to the pressure from the business world. And the education needs to happen on the side of the long tail of where it's going. Like as we talked earlier, there is absolutely 100% value, and I'm very excited about the ML aspects of it. But the long tail is what kills the product, and that needs to be educated as opposed to kind of swept under the rug, and getting fast to having a decent performance, because I mean 99% of the 99% of the planning problems, for example, are indeed trivial, because it's like I don't want to use the self-driving here, but I don't know, for aerial vehicles, they 90% of them they're flying straight in a straight line. There is nothing complicated.
And that will change.
Yeah, it's the long tail that kills us. There needs to be a proper education, and furthermore, I think there needs to be pointed to some examples from the past. Like when a while ago, when I just started robotics, the boom was about behavior-based robotics. If you go to a conference like ACRA, 99% of it was about behavior-based robotics. And, like, why do we need planning when there's behavior-based robotics? And that was because it was actually capable of solving some of those navigation, 95% of navigation problems. But then the other 5% was the killer of that. And now you go to ACRA and, there's not much on that level. So I think that education needs to happen, and not within the robotics community, but higher up to the executives and the investors. Unfortunately, that's not happening.
Okay, we have time for one last question.
Okay, cool. Yeah, finally. I'm coming from UCSD doing control motion planning. Here is my experiments. I tried a lot of different ML-based methods for motion planning. They have a structure like they have a model predict some kind of distribution in the space, and then using tree structure RT to explore the space, right? There's funny thing I found like half years ago or 1 year ago is that I tried couple of model. They read the point cloud as the obstacle, and it generates some Gaussian distribution telling RT where you should explore. And accidentally, I passed those obstacles as point cloud as all zero, nothing at all. And then when I run it, now which means that the model actually does not understand the obstacle at all, and then the performance is still better than a traditional algorithm. Even I add the point cloud correctly, the performance is the same. So I feel like the model might not understand the environment at all. It just learned a space that, oh, most likely this region is good to explore. Like I have a feeling that it gives me a feeling like it learned where is a self-collision-free space. It does not actually understand the obstacle. So like my opinion is that like ML is great, but like I don't feel like it is something that like which one is better. Like a traditional algorithm, ML, both of them can be like used together. Like ML is great for telling you which region is good to explore. I feel like it's too bad. Like people should pay the attention at the same time. It's not like something that okay, we should all focus on one part, right?
So very quickly, we had a big project funded by NASA, and there was a person there coming from a big aerospace company, a multinational company. And it was me presenting all of this MPC stuff, trajectory optimization, this and that. And he made a very, very uncomfortable question, which was, can I certify trajectory optimization? Right? And so, and that's, I think, one of the hard questions that we should be asking. in the planning community. And so when it comes down to these questions, right, like can you certify something? Then you have to go back and start thinking about, how can I interpret what a module is doing, right? And it's not about traditional versus ML, like you have to use whatever you need, but for as long as you are interpretable and you can explain what this module does and characterize input-output relationships, right? If I can characterize what the module does. So I think this is really the hard question when it comes down to, from my perspective. So, and that's not going to be a one approach fits all. That's not going to be one architecture works for everything. There needs to be more.
All I want to say, they say instead of thinking about the model or cost function or all these intermediate parameters, I will focus on my data sets. And that for them, they think it's much easier for them. And that's why they want to hire people who know ML or the language.
Well, it's much more straightforward, right? But also, I think, and maybe this is a challenge for all of us in the room, right? You can just do pip install PyTorch. It works great. You do 4 lines of code, you have a new model, right? And if you want to use any of the planning and control software, that's just not the case. And so there is an open question here to me of if we had better tooling, would this also be more accessible? Would there be more research in it? Could we find the new ways and could we overcome some of these challenges and develop these solutions? And if we do these hybrid approaches that I think everybody here is saying is probably the right answer, right? Does that help get us over the barrier? I don't know, right? But you're right. Like if I was starting a company right now and I wanted to make a sexy demo to raise some money, I would do behavior cloning 100% of the time. I also it would be terrified of actually deploying that in the long run. But I'm also a risk-averse academic who happens to like optimal control, so maybe I'm a little bit biased.
Usually classical people are the one who propose hybrid approach. The other people.
Taking all the way.
We are not that much willing to share.
And maybe that wins in the long run, but I feel like, they're over here, like we're sort of over there. There's the explainable AI people who are trying to bring some explainability into ML. Can we add some ML into that? We'll probably meet somewhere in the middle, and then maybe it ends up being called ML. I don't really care, right, what the name is at the end of the day. I just want to get to a result that I believe something about that is good.
I've had some luck working with some folks that kind of did their PhDs in pure imitation learning and started to incorporate like planning tools over time that I think would help is just showing them improved success rates, right? Improved generalization across complex tasks, right? As you move beyond just these simple tabletop manipulation environments. So I think you can definitely get to them. And it does help for simplicity purposes that you can view ML as a black box nowadays, even though the operation of a transformer is very complicated like a simulator, right? But I think many times if they're data-driven, just showing them data that shows this is actually better or can handle the long tail or edge cases might be a pathway towards, bridging that gap.
Actually, more recently, I see more and more papers and works, both in academia and industry, where even ML people start incorporating some of the aspects of planning. I mean, like diffusion policy, for example, to some extent is, the form of data-driven, but then you put in constraints, online constraints to generate something that says constraint. That's planning, right? The inference, like usually just to generate whatever the inference, but integrating some of the online actually was during the inference. And inference is a search, right? So there are some more and more, and I don't think it's infeasible to see that ML folks would also actually eventually stop looking at the combination.
I think machine learning people doesn't incorporate planning, they just give it a different name, right?
Yeah, exactly.
Test time scaling, what is that?
Yeah.
Isn't that just a search?
Yeah, it's different name, it's totally agree, right?
Yeah, all right, I think with this, we'd like to conclude the workshop. And
very
thank you, everyone. We'd like to thank all the speakers and the panelists. Great talks.